Well, welcome to another Talking Hand video, and this one is on escape velocity. Okay, now that's just out of the frame. Okay, let's just move this a little bit. There we go, like that. And for escape velocity, kind of imagine something like this. Here's the surface of the earth, here's you. Okay, and you throw a ball upward, and it comes back down. You throw it faster, and it comes back down. But it goes higher. Throw it faster, it goes higher and comes back down. Is there some big velocity where you throw it, and it goes away and never comes back? Well, that's called escape velocity. Okay, so let's look at the force of gravity. Force of gravity equals G m1 m2 divided by the distance between the two objects squared. We've had this before, and we know that work, which is energy, equals force times distance. But that's not really what it is. What it really is if you have a force and distance graph where the force is allowed to vary, right? And you find this area. Okay, this is energy in units of joules. Well, we could do that with this equation. So let's take a graph of this equation. Okay, we have force here. We have distance here, which is radius r. And if you graph this thing, G and M are constants, but it varies by the inverse square of r. That looks like a curve like that, asymptotic to both axes. Okay, and if we define some radiuses, this area over here, where this guy's newtons and this guy's meters, will give us units of joules. Okay, so to figure this out, we need to integrate this equation, G m1 m2 over r squared. Okay, and we could integrate it between some boundaries like r1 and r2, which you do on some problems, but for this we're just going to get a generic equation. So if I integrate that, the universal gravitational constant is a constant, the mass of the two objects is a constant, so that's going to get factored out. G m1 m2, and this just simply becomes r to the minus 2 dr. Okay, integrate this thing, and this thing integrates simply polynomial integration, so it's r to the negative 2 plus 1 over negative 2 plus 1, right? So that's r to the minus 1 over minus 1, or negative 1 times 1 over r. Okay, put this together with what we factored out. We have G m1 m2 over r. The negative sign is there, and this is the energy. A lot of times people use U, but I'm going to write potential energy maybe with sub G, something like that, for our equation. Let's not confuse this with this potential energy, which is equal to mgh. Okay, related, but this is for a different kind of problem, and quite often we will ignore the minus sign. Now, why is there a minus sign? Well, because when you move something closer, as radius gets smaller, the force of attraction goes up, not down. Okay, so there should be a minus sign there. For the most part, you could ignore the minus sign for many problems. Okay, so let's take a look at escape velocity. Okay, what we have is, if this is greater than, I'm sorry, that's incorrect. If this is less than the kinetic energy we give the ball. So we're throwing this thing up in the air, and we're going to give the ball some kinetic energy. Okay, what will happen is we're going to define the two m's. So we'll let this guy be the ball, we'll let this guy be the mass of the earth, and we'll let this guy be the ball because we're throwing the ball up in the air. Notice the mass of the ball doesn't matter. Okay, and we could solve this for the velocity of the ball. Whatever this particular velocity is, if we throw it faster than this velocity, the ball goes up and never comes back, and that's called escape velocity. Okay, so we'll multiply both sides by 2, and that leaves us v squared, no square root. So we'll have g, mass of the Earth, divided by, oops, that's r to the 1, not r squared, r, okay, multiplied by 2. This is v squared, and so we'll square root both sides. Okay, and that's our escape velocity. Now you could put anything there. It doesn't have to be the Earth. It could be a star. It could be the moon. It could be whatever it is, and the radius of the planet. Okay. So, for example, if you wanted to calculate the escape velocity of the Earth, and you guys should do this, the mass of the Earth, okay, is 5.98 times 10 to the 24th kilograms, and the radius of the Earth is 6.37 times 10 to the 6 meters, and we know universal gravitational constant is 6.67 times 10 to the minus 11th, and units are kilograms, meters squared. Oop, am I off the frame? I am off the frame per second squared. Let me show you that. Okay, I'll move it back down. Here we go. Let's go over that again. So the mass of the Earth is 5.98 times 10 to the 24th. The radius of the Earth is 6.37 times 10 to the 6th. And g is 6.67 times 10 to the minus 11th. Now, what if you did this? What if you took the same equation? I'm going to move this over here right now before I start this time. Okay, and we take the same equation, g m1 m2 over r, and we set this thing equal to 1/2 m. Okay, and one of these m's will cancel out. Let's just let this be m1. Okay, and what we're going to do is we're going to pick for our velocity the speed of light, c for the speed of light. And so this could be an escaping photon, which has no mass anyway, but we'll notice it goes away. And this, if we're not letting light escape, let's just say that we'll make this force greater, is the mass of a black hole. Okay, or if we take a mass of something that's crunched to such a sufficient density, we could find this radius r, and that radius r is called Schwarzschild's radius. Okay, and so what I would like you guys to do is solve this for r. Right, this thing right here, and there's going to be some problems to go with this, and that is all for this one.